So let's go over an example of approximating the ionic radius of an ion using Slater's rules and how we can use that to come up with a trend. So in the example shown here, what I'm asking is to arrange all the 5 ions that you see here on the left side of the screen in increasing order of ionic radius. That means I want you to go from the smallest ionic substance to the largest one. And the way I have arranged aluminum 3 plus, phosphorus 5 plus, germanium 4 plus, indium 3 plus, and antimony 5 plus is the same order as you find them in the periodic table. So the first thing you could do is use the regular trends. In terms of increasing size, you know that the size will increase going from right to left and also going from top to bottom in the table. So what this tells you is that phosphorus 5 plus should be automatically the smallest species in this set of 5 ions, and indium 3 plus should be the largest one. But the problem becomes, yes, and here we go, phosphorus 5 plus is the smallest one. The problem becomes the 3 ions right here, aluminum 3 plus, germanium 4 plus, and antimony 5 plus, because we have different properties affecting each other. We have on the one hand elements that are moving farther to the left, making them bigger, but they're also all the way up, making them smaller. And then we have other elements or ions that are all the way down, making them bigger, but then they are all the way to the right, making them smaller. So then the question becomes, well, which trajectory wins here? Going sideways or going up and down? And what we're going to do is use Slater's rules to answer this question. And I'm going to include indium 3 plus, which is going to be the largest species, just to show you that the trend works pretty well. But I will exclude phosphorus 5 plus because that one is guaranteed to be the smallest. And at the end, I'll show you that it is the smallest anyway. Alright, so we're going to do the calculations for aluminum 3 plus, indium 3 plus, germanium 4 plus, and antimony 5 plus. And that means that we'll have to come up with electron configurations for each one of these ions. We'll have to then group them according to Slater's rules, meaning that the s and p orbitals of the same energy level will be grouped as one thing. Then we'll calculate the shielding constant for the valence electrons, the group that is farthest to the right in the configuration. From there, we'll calculate the effective nuclear charge, and once we get that, we'll then go ahead and calculate the ionic radius of each of these species. Alright, so here we go. For aluminum, the configuration, including the Slater grouping, is 1s2, 2s2p8. And I encourage you to go through the process yourself to arrive at this point. I'm kind of bypassing all the little steps that takes us there. But it will be good practice for you to go through this on your own. Now, indium 3 plus, if you get all the entire electron configuration, remove 3 electrons, and then group s and p's of the same energy level, you're going to get the following trend. And also, you got to remember that you got to group everything in increasing order of principal quantum number. So all the orbitals of energy level 3 should appear first. All the ones with energy level 4 should appear thereafter, right? So that's one of the things that you have to get comfortable with in terms of coming up with these groups. Now, this basically means that for indium 3 plus, we will go all the way to 4s, 4p8, and then 4d10. And those are 2 separate groups altogether. For germanium 4 plus, you'll have the 1s2, 2s2p8 group, 3s3p8, and 3d10. And for antimony 5 plus, you have the 1s2, 2s2p8, 3s3p8, 3d10, 4s4p8, and 4d10. So I recommend that you go through the exercise of arriving at these particular electron configurations and Slater groupings. Alright, now with that in hand, what we're going to do is calculate the shieldings of each one of these ions, and we focus on the valence electrons only, so the group farthest to the right. So for aluminum 3 plus, we're going to be looking at the 2s2p electrons, and as such, we're going to concentrate on the left box here, the sp box within the Slater rules. And that says that for the same group, we shield by 0.35, being one quantum number less, we shield by 0.85, and being more than one quantum number less than the valence electrons, we shield by a full value. Okay, so looking at this, we have 8 electrons in the same group. 7 of them will shield with a value of 0.35, as shown by Slater's table. And then we have 2 electrons, which are one group to the left, so those 2 electrons will shield by 0.85. If you do the calculation, you're going to find out that this equals 3.10. Alright, now let's do the same thing for indium 3 plus. We concentrate on the 4d electrons, since that's the last group on this series, and because of that, we're now going to focus on the df set within the Slater table, which means that for electrons in the same group, we shield with a factor of 0.35, but any electrons that are on groups with a value of n that is 1 or more less than the actual value of the valence electrons, we're going to shield completely. That's the big difference between the D and F electrons versus the S&P. Slater assumes that D and F electrons just don't penetrate towards the nucleus very well, so they get shielded completely. Alright, so what that means is that even though you have a lot of groups right here, the picture is actually rather simplistic. Because, okay, you have 10 electrons in the D set, so 9 are going to be shielding with a factor of 0.35 onto the 10th one. But then everything else that's to the left side, as you can see here, is going to shield completely. So all you have to do is add the numbers. 2 plus 8 is 10. 10 plus 8 is 18. 18 plus 10 is 28. And 28 plus 8 is 36. So you simply add up all those values and multiply by 1, since that's what it has to happen according to Slater's rules for the electrons in terms of the shielding constant calculation. So when you add all these values together, you'll get 39.15. Similarly, for germanium, we're also dealing with the electrons, so we still stick with the df column in Slater's approximation. And like we did before for indium, 9 out of the 10 electrons will shield with a value of 0.35. And after that, you just add up the rest of the electrons to the left. So 2 plus 8 is 10, 10 plus 8 is 18, and 18 times 1 is the overall shielding arising from those electrons. When you add the groups together, you end up with 21.15. Alright, now for antimony, same idea. The last group is a D group, so you still deal with the DF column in Slater's rules. And once again, out of the 10 electrons, 9 shield with 0.35. And then at the end, you simply add up the rest of the electrons to the left of the 4D group, which is exactly the same as the indium 3 plus example. We have 36 electrons total to the left, which shield with a factor of 1. Upon multiplying all the numbers together and adding them, you end up with 39.15. Okay, now what we're going to do is subtract all of the shielding constants from the atomic number of the ion. In the case of aluminum, we're talking about 13. In the case of indium, it's 49. Germanium is 32, and antimony is 51. So we write down all of those atomic numbers, and now we subtract the shielding constant from the corresponding atomic numbers. When you carry the subtraction forward, you'll find out that the effective nuclear charge is 9.90 for aluminum 3 plus, 9.85 for indium 3 plus, 10.85 for germanium 4 plus, and 11.85 for antimony 5 plus. So the last thing that needs to be done is to use the Bohr approximation of the atomic radius. In this case, we'll be looking at the Ionic radii, and also the principal quantum number, the effective principal quantum number table. So looking at aluminum, we are dealing with 2s and 2p electrons. The value of n for 2 is the same as n star, or rather n star is the same as n. So we basically multiply 0.529 by 2 square, which is what we see here on the equation for the Bohr radius. And we divide this by the effective nuclear charge of aluminum 3 plus, which is 9.90. And when you carry on this multiplication and division, you find out that the approximation is 0.239 angstroms for the size of aluminum 3 plus. Now for indium, similarly, we do the same thing, but here is the little trick, or not really trick, but the one thing you have to be aware of. We're dealing with a 4d electron set as the valence set, and because the value of n equals 4, now take a look at the table here. When n equals 4, n star has to be 3.7, so you have to multiply 0.529 not by 4 squared, but rather by 3.7 squared. And you divide this by the effective nuclear charge, which is 9.85, And when you carry the multiplication and division, you find out that the ionic radius is 0.735 for indium 3+. Doing the same thing for germanium 4+. Now we're dealing with 3D as the valence group. For N3, N star is also 3, so we simply multiply 0.529 by 9, or 3 square, and divided by 10.85, which is the effective nuclear charge. The overall radius, ionic radius, is 0.439 angstroms. And for antimony 5+, the valence group is 4D, so we multiply 0.529 by 3.7 square, and we divide it by 11.85, which is the effective nuclear charge, and we find out that the value is 0.611. Alright, now the beauty of this is that even though the values are not exact in terms of being close to the true values, the trend is pretty much constant with the trend that you see in the periodic table. So looking at this thing, you can see that out of all the numbers, the one that is the smallest is aluminum 3+. So that will be the next one in the series. After aluminum 3+, the one that is third smallest is germanium 4+. Germanium 4+ is actually 0.439 according to this, and that will be followed by antimony 5+, which is 0.611, and that will end with indium 3+, which is what we predicted to be the longest or largest ion in the series. So Slater's rules presents a really neat way of looking at this, and just to kind of conclude and give you the full-on picture, if we look at the periodic table and the actual values for these ions, we find out that yes, phosphorus 5+ is 0.52, it is the smallest one in the series. Aluminum 3+ is 0.67, which is the next smallest one. Germanium is 0.67, so actually they are roughly the same value. And within the approximation, we have aluminum and germanium right next to each other. So for my purposes, that's good enough. Within the error, probably this works out rather well. After germanium, the next ion that is the larger one is antimony with a value of 0.74, and finally we end up with indium with a value of 0.94. So the trend that we got here using Slater's rules and the regular trends of periodicity work out fantastically. So I personally like this a lot, and you are expected to see this in future assignments. Okay, we'll stop right here and we'll continue on the next video.